covering lesson 1.4 scaled relationships, starting on page 23. Our learning goal for today is to be able to find relationships between scaled copies. More specifically, we'll be covering what is called corresponding distances. Now, before we do that, let's do a quick review and the warm-up. So if you guys remember, we are studying scaled copies. Scaled copies are copies of a figure in which all lanes have been increased or decreased by the same scaled factor. Now we have also covered something called corresponding parts. Corresponding parts are parts that appear in identical places in similar figures. Now when we studied both these together, we found out that corresponding angles in scaled copies are also identical in measure. Now let's go ahead and start our one. For each of the polygons is a scaled copy of the other. So automatically we know that their angles or their corresponding angles are identical in measure and size. Now, they're asking us in question 1 to name two pairs of corresponding angles. What can you say about the sizes of these angles? So let's go ahead and analyze our three figures. Now, I'm going to list my first pair right over here first. Now remember, corresponding parts are just identical places in similar figures. So if I concentrate on my first two figures, I notice that it has this angle right over here. Now that angle is angle C. The corresponding angle in figure 2, or my second, would be angle G, because they appear to be in the exact identical place of each other. So that would be what I would say would be my first pair. Now let's go ahead and name a second pair. Now for my second pair, I'm going to focus on my second figure and my third figure. Now if I look at the bottom angle created here, that is angle E. Now its corresponding angle in figure 3 would be the bottom angle as well, so that would be angle I. Now what can I say about the sizes of these angles? Now if you guys remember what angles are, angles are just two line segments that meet at a common endpoint. So if I have one line segment and another line segment, both of these line segments meet up in the same endpoint. We usually call that endpoint a vertex. Now, depending on the measure, how open those angles are, we actually have classifications. The three most common ones that we do is a 90-degree angle, and that one is one of an angle that create a 90-degree angle, usually shown with a little box. Now if we have a pair of angles that's more than 90 degrees, we're going to have an angle that looks something like this. We call those angles obtuse angles. And they are more than 90 degrees. Now our third is if we have less than 90 degrees, a measure of less than 90 degrees, we call acute angles. So if I look at my first pair of corresponding angles, if I'm analyzing those and just kind of looking at those, I can notice that those two angles would be acute because they appear to be less than 90 degrees. Now if I go ahead and look at my second pair of corresponding angles, angle E and angle I notice that those also appear to be acute. So I can see that the two pair of angles I've chosen are actually both less than 90 degrees. Question 2, they're asking us to check our prediction by measuring at least one pair of corresponding angles using a protractor. Record your measurement to the nearest 5 degree. So what I'm going to do is move over to my dot cam to be able to use a protractor. Now, if I look at my corresponding angles, I'm going to start with angle E here. Now, I've already marked that it's 52 degrees. Now, I'm going to show you how to use your protractor to be able to know why it's 52 degrees. Now, whenever you have a protractor, you always want to line up the vertex, the point where your two line segments of your angle meet, with the center of the protractor. So that's the first thing I'm going to do. The second thing you want to do is line up one of your line segments with the start of the protractor. Now, the first one that I feel like is easier to do would be this little left bottom piece.
Now notice that while I'm lining them up, I'm also keeping my vertex at the center of the protractor. Now, whenever you're measuring an angle, remember, you're measuring the opening of the two line segments from the vertex. So if I line up here, I notice that I'm at 0 degrees and not 180 degrees, so I'm going to use my scale above. I'm going to try my best to see how open my second line segment is. And I see it's around 52 to 53 degrees. So I would say that measurement is 52 degrees. Now let's go ahead and measure its corresponding side of my third figure. Now the corresponding here would be I. Now before I actually measure, I know that these are scaled copies, and I know that angles within scaled copies are identical in size. So I expect it to be 52 degrees. Now let's double check using our protractor. Using the same method, here's the center of our protractor. I'm going to go ahead and line it up with the vertex of the angle I'm trying to measure. And then I'm going to go ahead and line up one of the line segments with the start of my protractor. Now you can see here that I don't quite know exactly what degree it is because my line unfortunately only ends here. Now a quick trick that you could do to help you out is just to extend it. Use any straight edge you have, extend it as much as you please, and go back and see if that helps at all. Now you can see here that this helps greatly, and I can see that, hey, it's roughly about 52 degrees as well. So that means that this angle is 52 degrees as well. Now the cool thing is that if you choose any corresponding parts, the measure is always going to be the same if you have scaled copies, which we know we do. Alright, so now that we've checked that corresponding angles and scaled copies have the same measure, let's go ahead and flip to the next page. Now the next page is asking me, or telling me that each of these polygons is a scaled copy of each other. Now I double checked with the front page, and these are the exact ones they gave us on the page before. Now they're also letting us know that we've already checked that their corresponding angles have the same measure. Now looking at problem 1, the side lengths of a polygon are hard to tell from the grid, but there are corresponding distances that are easier to compare. Now, before we dive into the actual problem, I want to remind ourselves that we are dealing with scaled copies. So that means that there exists a scale factor, some number, that when I multiply all the lengths of my original would equal the lengths of my scaled copies, or their corresponding parts would. Now, if I were to check to see what that scaled copy is, what that scale factor is, if I looked at my copies and my original, it is pretty hard to determine what the side lengths are. For instance, if I look at side length D to C, I can see here that this distance is pretty hard to measure since it's not nicely in the grid. And this goes to say the same for every side length of this polygon on this particular grid. It would all be really hard to know the exact measure. So what can we do? Well, there's this concept of what is called corresponding distances. Corresponding distances are distances that appear in identical places in two similar figures. So let's go back to our question. Identify the distances in the two polygons that correspond to DB and AC and record them on the table. So let's start with the very first one. The distance that corresponds to DB. Now they're telling us that the length of DB is a side length of 4. Now if I were to locate it on my first figure, I notice that DB is right here. Its measurement would be from that side to that side, and I notice that it has a measure of 1, 2, 3, 4. So it checks out. DB does have a side length of 4. Now if I were to locate its corresponding distance in figure 2, well, where is that distance identical to? Well, I would say it's from H to F. Now, in measuring that side length, 1, 2, 3, 4, 5, 6, I would know that that is a side length of 6. Now, looking at the corresponding distance in figure 3, I would say it's from L to J, which is a distance of 1 and 2. So LJ is a distance of 2. Now, those are the corresponding distances of all three figures. Let's go ahead and find the corresponding distance of AC now. Now, just double checking, where is AC? It's in my first figure. A is here, C is there, its distance would be that. So that would be 1, 2, 3, 4, 5, 6. It would be a distance of 6, which checks out. Now, the corresponding distance in figure 2 would be from G to E. So just to highlight the distance, let's go ahead and count it. 1, 2, 3, 4, 5, 6, 7, 8, 9. So GE has a distance of 9. Now, in our third figure, its corresponding distance would be from K to I. That distance would be 1, 2, and 3. We have our table complete. Let's go ahead and move on to question 2. They're asking us to look at the values in the table. What do we notice? Now, just to make it a little bit cleaner, I'm going to go ahead and rewrite my table to the left there. Now, notice that you have space to the right where you could also copy your table. So, to make it easier on me, I noticed that they're asking me what is the distance that corresponds to DB to the left of my table. Now, when I look at DB, I notice that angle is the horizontal distance from D to B. So to notate it, I'm just going to write it down as horizontal. Now, if I look at my distances that corresponds to AC, AC appears to be a vertical distance going up and down. So I'm going to notate that with a vertical line. So that way it's a little bit easier for me. I'm going to go ahead and copy my values. I notice it's 4, 6, and 2. And then do the same thing with my other values. So now, what is something that we notice? Now, this might bring you memories back in 6th grade when you guys were talking about scale factors. Now, if you look at this table and also look at your guys' figures, you'll notice that something pretty cool happens. Now, if I were to think of my figures first, I would say, okay, if I have corresponding lengths, corresponding distances, there exists a scale factor that multiplies all the corresponding lengths to equal the other side. So, in this instance, let me look at my table. Does there exist a scale factor that I can multiply 4 by to get it equal to 6? Now, to help us out, I'm going to write my equation over here to help us out. 4 times what value would equal 6? And notice I'm having trouble figuring out what that value is. But just like other multiplication activities, I know that I can use other skills that I know. For instance, if 2 times 3 equals 6, and I'm trying to figure out what that value is at 3, what I can do is take my 6 and divide it by 2, and I'll notice that I'll figure out what times 2 would give me that value of 6. So doing the same thing over here, I'm going to take my value of 6, and I'm going to divide it by 4. Now, I'm not quite sure what 6 divided by 4 is, so I'm going to use my calculator over here. I notice I end up with 1.5. So, I know that 4 times 1.5 equals my 6. Now let me go ahead and double check this with my other corresponding distances. So 6 times what value would equal 9? Well, remember that this is pretty tough. I don't know what would multiply 6. It's going to be a fraction, but I know my multiplication is the same thing as division. So I can go ahead, take my 9, divide it by 6, and figure out what that number is. And you'll notice that it equals 1.5 as well. Now, I've seen a pattern here that if I look at my horizontal distance in relation to my vertical distance, there exists a scale factor that I can multiply my purple to get my blue. Now, let me go ahead and see if it's true throughout. I'm going to take this 2 and I'm going to multiply by 1.5 just to double check to see if I get a 3. And you notice that it checks out. So, what have we covered? That not only can we pull information from corresponding distances to help us figure out that scale factor,
But we could also create a table to make it a little bit easier on us to look at those patterns and recognize them. How to use tables to help us find scale factors. Let's go ahead and move on to the next page. So on the next page, question 3 is telling us that the larger figure is a scaled copy of the smaller figure. So automatically I know if this is my scaled copy and this one's my original, I know that there exists a scale factor, a number that multiplies all my corresponding parts and distances on the original to equal the corresponding distances or lengths on my scaled copy. So let's go ahead and read question A to see if that helps us. If AE equals 4, how long is the corresponding distance in figure C? So if I were to look for AE, which is right over here, they're telling us that that side length is 4. And they're asking us what would be the corresponding distance in the second figure. So to solve this problem, we're going to go ahead and set up a ratio using the tables and solving them just like we did in the problem before. So let me go ahead and set up my table. To the left of my table, I'm going to put my original distances. And to the right, I'm going to use my new corresponding distance of my scaled copy. So first thing that I notice is that they did give me corresponding sides with known distances. I noticed that in my original, I have a value of 6, and in my scaled copy, I have a value of 15. Now they are asking us, hey, if you know that AE has a distance of 4, what would be the corresponding distance of HL? So that is what I'm looking for. Now, just like we covered on the page before, we know that there exists a scale factor that multiplies my original distances to equal my corresponding distance of my scaled copy. So I could go ahead and focus on that value of 6 and say, okay, what can I multiply 6 by to be able to equal 15? I'm going to do that over here to the side to help me out. 6 times what value equals 15? Now on top of my head, I cannot know that value, but what I could do is take my value of 15 and divide by 6 to figure out what that value is. That scale factor that will give me that 6 to equal to 15. So 15 divided by 6 equals 2.5. Now, just like we figured out yesterday, we know that if I multiply my original by my scale factor of 2.5, it's going to equal the distance of my scaled copy. And I can do this for every single value of my original, as long as I multiply. So to figure out what that value is, I'm going to take that 4 and multiply it by 2.5, and I'll end up with 10. So that means that my distance, HL, would equal 10. Now, looking at question B, if IK equals 5, how long is the corresponding distance in the first figure? Now, the first thing I'm going to do is go ahead and locate where IK is at. Now, if I were to look for IK, I notice that IK is down here. Now, just to extend my table, I'm going to go ahead and extend that, so that way I can do my problem below. Now, where is IK? I notice that IK is right over here, and it is part of my scaled copy. Now, that distance is 5, so that means it's going to belong in my scaled copy column of my table. Now, this is where things can get a little tricky, because notice that in order to go from my original to my corresponding parts of my scale, I would have to multiply by 2.5. But this time I wasn't given the original, I was given my scaled copy. So that means I am working backwards. And what would be the opposite of multiplying by 2.5? It would be dividing by 2.5. So taking that 5 and dividing it by 2.5, 5 divided by 2.5, I would end up with a value of 2. So I know that its corresponding distance, B and B, would be a value of 2. Now
let me clean that up because it looked a little bit messy. 2.5 to work backwards. So notice that whenever we have our values of our original scaled copy in the table, it makes it much easier to work and find distances from original to scaled copy, or going from our scaled copy to our original by knowing that the scale factor is either going to multiply or divide depending on which way you are working. Let's go ahead and turn the page. So activity 4.3, scaled or not scaled. Here are two quadrilaterals. May says that polygon ZSCH is a scaled copy of polygon XJ, Y, and N, but Noah disagrees. Do you agree with either of them? Explain or show your reasoning. So according to May, this would be our original figure, and this would be the scaled copy. Now, knowing what I know of scaled copies, there are a couple things that have to be true. One of them is that the image cannot be distorted or changed. It's literally just smaller or bigger in comparison to one another. Now, given the eye test, if I look at my original to my scaled copy, these images look pretty similar enough to say that they could be a scaled copy. So, image cannot be distorted. Now, a second thing that has to happen is that there has to exist a scale factor in which all the corresponding parts or corresponding distances have been multiplied, so that way my scaled copy distances equal my original. So I know that there has to exist some type of scale factor. The third thing that I know is that the corresponding angles in scaled copies are identical. So that means that the corresponding angles of the original have to have the exact same measure of my scaled copy. Now, to be honest with both of them, I don't know if they're scaled, but I do know what I can do to check to see if it's a scaled copy or not. Now, the first thing they're going to have us do is record the distances, so I'm assuming that they're going to have us double check to make sure that there exists a scale factor that multiplies all of the distances or lengths of my original to equal my scale copy, aka there exists a scale factor. So let's go ahead and start with the very first one. They're asking us to find the horizontal distance from x to y. So here's x, here's y. The distance would be 1, 2, 3, 4, 5, and 6. Now, looking at polygon ZSCH, ZC, the distance from Z to C would be 1, 2, 3, and 4. Now, looking at the vertical distance in my first polygon, J to N, I would have a distance of 1, 2, 3, 4, 5, 6, 7, 8, and 9. And its corresponding distance in our scale copy, or what we're checking, would be 1, 2, 3, 4, 5, and 6. Now that we've recorded the corresponding distance from the table, let's double check to see if there exists a scale factor. Now, looking at this, 6 times what value would give me 9? Now, I'm not quite sure, so I'm going to go ahead and write that statement to the left. 6 times what value equals 9? Now, I can see that whatever this value is, it's going to have to be 9 times 6, 9 divided by 6. So 9 divided by 6 is going to give me 1.5. So I know that if I multiply 6 times 1.5, I would end up with 1.9. Now, if this is truly scaled, I should be able to multiply 4 times 1.5, and I should get a 6. Now, let me go ahead and double check that. 4 times 1.5 equals 6. So far, everything checks out. There is a scale factor, and that scale factor would be 1.5. Now, remember, like I said earlier, just because the images look to not be distorted, just because there's a scale factor, doesn't mean that these are copies of each other, or scaled copies of each other. We still have to double check to see if the angles are the same. And that's what they're going to ask us to do in question 3. Measure at least 3 pairs of corresponding angles in x, j, y, n, and z, s, c, h using a protractor. Record your measurements to the nearest 5 degrees. What do you notice? So I'm going to go ahead and move on to my dot cam to be able to use my protractor. Okay, so now that I have moved on to my dot cam to be able to measure the angles, let's go ahead and remind ourselves what they're asking us. Now they're asking us to measure at least 3 pairs of corresponding angles between the 2 polygons. Now the angles that I am going to focus on are angle N and its corresponding angle, which would be angle H. And then I'm going to go ahead and do angle C and its corresponding, which would be angle Y. And then last but not least, I'm going to go ahead and do angle J and angle S. Now keep in mind that it doesn't matter which angles you use or the order, all it matters is that you're using corresponding angles. So knowing what I know that these corresponding angles must have the same measure. These ones also must have the same measure, and since these are corresponding, they should also have the same measure as well. Now what I'm going to start with is finding the measure of angle N. Now here's angle N, here's my protractor. I'm going to go ahead and line up the center of my protractor with the vertex. Now looking at that one right there and lining it up as well, I notice that it's pretty hard to see what the measurement is, but I could see if I were to stretch it out, it'd be roughly about 140 degrees. Which visually looks to be a match because I noticed that angle N would be an obtuse angle more than 90. Now let's go ahead and measure angle H. Now if I were to flip my paper to the side to be able to measure a little easier, here's the center, there's the vertex. Let me line my lines up. Now I notice now that I'm opening up to the right. So if I were to look at that measure here, I notice that angle H, which would be right here, is about 110 degrees. Now, although it's obtuse, I can clearly see that these two angles are not the same measure. This one is much shorter in measure. So automatically that tells me enough that these two figures are not copies of each other because the angles are not the equal measure. Now let's just go ahead and see what would happen with these angles. Now I'm going to go ahead and measure angle C. Here is C, there's my vertex meeting up and my line segment meeting up. If I were to measure it out using the 0 scale, I would roughly be about 80 degrees for angle C. Now looking at angle Y and lining it up, I would be roughly about, using my 0 degree, I would be around 76 degrees. So you see that those differ as well. Now just to follow directions and measure 3 of them, let's go ahead and do J and S. Now J is right over here. I can see that this one's going to be acute. If I were to line it up, start with my 0 scale, I notice that angle J is going to be around 42 degrees. Now let's go ahead and measure angle S. Starting with my 0, I notice that it would be roughly about 45 degrees. So what do we notice? The angles are not the same measure. Now, an important key feature that I forgot to leave out is not only that the angles are not the same, but the corresponding angles are not the same measure. And we know that in order to have a scaled copy, not only do we have to have a scale factor, and not only does the image not have to be distorted, but the angles also have to be the same. So do these change our results in the first question? I would say yes, because when I looked at the first question, given it the eye test, it looked to be scaled, but as we dove in deeper, we finally realized that it was not. So now that we know that these two polygons are not scaled copies of each other due to their angle measure, let's go ahead and flip to the next page. Now on the next page, you notice they gave us 2 more quadrilaterals. Now Chiron says that the polygon EFG is a scaled copy of ABCD. So with that being said, our original would be ABCD, and our scaled copy would be E, F, G, H. Now Lynn disagrees. Do you agree with them? Explain or show your reasoning. So again, just giving a quick eye test, the image cannot be distorted if it is a scaled copy. So giving a quick eye test, I could clearly see that these look to be pretty similar shapes. I feel like there's a possibility that this could be a scaled copy. Now, keep in mind that we also have to make sure that all the angles are the same, or the corresponding angles have the same measure. Now looking at D, I have 120, H has 120, C has 120, 120. It looks like, by visually inspecting it really quickly, that all the angles are exactly the same measure. So far these do appear to be scaled. Now, last but not least, let's double check and make sure that there exists a scale factor, some number that multiplies all my side lengths in our original to equal the corresponding parts of my scaled copy. Now, what I like to do is to look for the side lengths that's a little easier to do math. If I notice here I have a 2 and the corresponding part would be a 1. Well, what would be the scale factor? What would be the multiplier? What would I have to multiply in order to get 2 to equal 1? So just to be consistent, let's go ahead and write out that statement to find out what that scale factor would be. 2 times 1 value would equal 1. Now, I'm not quite sure what multiplier it would be, so I'm going to go ahead and take my 1 and divide it by my 2. And I can see here that my response would be 1/2. Or, if you like decimal form, 0.5. Now remember that every corresponding side has to be multiplied by 1/2 or 0.5. If not, unfortunately, we do not have scaled copies. So looking at CB and its corresponding side GF, I would have to multiply 4 by 1/2, which would give me a value of 2, which isn't the distance that I have. So you can see here that unfortunately there is no scale factor throughout. So that means that this quadrilateral is not, these quadrilaterals are not scaled copies. So with that being said, we are done. Don't worry about, are you ready for more? So looking at activity 4.4, here are 2 pictures of a bird. Find evidence that one picture is not a scaled copy of the other. Be prepared to explain the reason. Now the main thing here again is to notice our 3 reasonings or 3 facts about having scaled factors. Now this one in particular, I noticed that the image is not exactly the same. It's a little bit distorted. And where I notice it a little bit more is in the head of the 2 pigeon. You can see here that one seems to be a little bit more flatter than the other. So I can see there that with that alone lets me know that, hey, this is not a scaled copy. Somehow one length has been stretched a little bit more than the other. All right, so let's go ahead and flip to the next page. So a quick summary, when a figure is a scaled copy of another, we know that all distances in the copy can be found by multiplying the corresponding distances in the original figure by the same scale factor, whether or not the endpoints are connected by the same. For example, these 2 polygons are a scaled copy of each other. The scale factor is 3. The distance from T to X would be 6, which is 3 times the distance from B to F. Now we also know that all the angles have to be the same measure as the corresponding angles in the original. As in these triangles, the measures are all the same. Now, these observations can help explain why one figure is not a scaled copy of another. For example, even though the corresponding angles have the same measure, the second triangle is not a scaled copy of the first rectangle, because different pairs of corresponding lengths have different scales. So you can see